Okay. Well, let's start because we have a schedule and people will still be joining us, but out of respect of everyone who is on time. So I'm gonna just do a short introduction and then I will pass you the floor. Okay. So recording. So hello everyone, and welcome to another talk in our webinar series. This webinar is also being streamed live on YouTube. You can find the link on our website, or you can access it on our YouTube channel, LIneA MCTI. So today we have the honor and pleasure of having Dr. Laure Ciesla from the CNRS at the Laboratoire d'Astrophysique de Marseille. Dr. Ciesla research lies in the framework of galaxy evolution, studying the star formation history of galaxies by modeling their spectral energy distribution. Scientific interest, her scientific interest extends to the UV to radio emission of high redshift galaxies and active galactic nuclei. So Dr. Ciesla, thank you very much for being with us today and for being so kind and having accepted to give us a webinar talk on such an exciting topic. The floor is yours.
Thank you very much. No, it's a real pleasure to be here and fun to be on through Zoom, I would say, and present my work to you. So it's related to the star formation histories of galaxies and how we can reconstruct it from observation, especially broadband photometry. What are the challenges and what do we need to do that and what do we want to do that? So this is what I will try to explain here. So just to start and guide you to the questions that I am interested in is first, if you look at a typical field of galaxy, just a random one, the first thing you notice is that galaxies are very different in terms of morphology, but of colors. You have this nice spiral here, which is mainly blue, if we can say, and we have here something more red with like a spheroid, so something an elliptical galaxies. So if you look at the sky for the first time and you see galaxies, the first thing you want to do is classify them. And you can classify them by colors, like here in this color diagram. So this is just a difference between the U-band image and the R-band image. And here you have on the x-axis the mass of your galaxy. And what you can see is that galaxies are distributed mainly into two big regions. You have the blue cloud of the star-forming galaxy, and the red sequence, which is here, where you have passive galaxies like the elliptical that we see here. And in between, you have some galaxies that are in transition and that we call the green valley. And one of the main questions that we have is how galaxies move from this blue star-forming cloud to the red sequence of passive galaxies. So to try to answer this question, we have two observational evidence that help us to try to answer this. And the first one is that we find more passive galaxies in dense environments. You have here an image of the Virgo cluster and the nearby cluster, and you really spot here the numerous elliptical galaxies, the red one. So you have more passive galaxies in very dense environment compared to the field. So you have a clue that the environment plays a role here in making galaxy becoming from star forming to passive, to stop the star formation activity. The other evidence that we have, observational evidence, is that the more that massive galaxies become more rapidly passive. So here the mass in terms of evolution plays a role into quenching galaxies star formation activity. So to try to put some constraint on this and try to understand these two clues, we have some scenarios for possible mechanisms responsible for the quenching of the galaxies. So here we try to list a few of them. Just to give you example, you have here mechanisms related to the gas, because of course, to have star formation, you have to have the gas in your galaxy, which is the fuel of star formation. So you can imagine that if a galaxy stops forming stars, it's because something happened to the gas. Maybe there is no more gas. So this can happen in different way. You can see here a galaxy, and we expect that some infalling of cold gas come onto the galaxies from the outside region, and fuel the galaxies to help it continue forming star. But what you can imagine is that this inflow are for any reason stopped, and then the galaxy doesn't have any more supply of gas. So you can see on this little cartoon that at some point gas accretion is stopped. So you still have some gas in your galaxy that is forming star, but little by little, there won't be any more gas. It will be consumed. And at the end, the galaxy will be passive. So this is what we call strangulation, for instance. And this is a slow process because you have to consume the gas that is already there in the galaxy. So it will take time to consume the gas and then become passive. So this is one proposed scenario, but then you can have a fast process. So you have here a galaxy that is part of a cluster. And what you see is that the galaxy is completely disrupted. It's what we call a jellyfish galaxy. So this is due to the galaxy entering the intracluster medium, which is very dense and hot. And then the gas inside the galaxy is stripped out of the galaxy. It's a strong mechanism that can also remove part of the dust and even stars when it's very strong. And you can see on the same cartoon that you have the gas accretion and then it stopped, but worse, the gas is removed from your galaxy. So what you have is just the star, more or less. So you don't have this process when you consume the gas present, because here the gas is removed. So rapidly you become passive. There is no more gas, so no more star formation. There are other mechanisms that are possible for to explain galaxies quenching, other than just some affecting the gas. You can have some feedback processes like nuclear processes. It is believed that the AGN could play a role into quenching the star formation of galaxies. You can imagine that the powerful jets that we see and the powerful outflow coming from the supermassive black hole in the center could have an impact on the gas surrounding in the galaxy host. So this is something still discussed. So this could have an impact and a role. You can think about also the feedback from stellar population here, where you have this massive star that have been formed through a violent episode of the star formation. And then you have the whole bunch of supernovae that expels the gas that is surrounding. So this could affect also the star formation in your galaxy. And then you have morphological processes where in this galaxy you have a bar, and we observe some effect of the bar in the bulge of your galaxy, impacting the distribution of the gas and how it will, and it could affect the star formation itself. And then, of course, you have the fusion process where you have two galaxies merging together. Then you expect to have a burst of a starburst, a burst of star formation. And then, of course, because you have all these stars that have been formed in a relatively short time, then the gas is consumed. So you expect after that there will be a quenching of star formation. And then another possibility is just that maybe some galaxies, just for any reason, start to form star but less efficiently, and then slowly become passive. So this is another interpretation. So I'm coming back to this diagram. So just to remind that we want to understand how galaxies come from the star-forming cloud to the blue to the red sequence. And another way to look at this distribution is to have a look at the star-forming main sequence, the galaxy star-forming main sequence. So you have here on the y-axis the star formation rate of the galaxies, and on the x-axis you have the stellar mass. What has been found now since about 15 years is that most of the galaxies are lying on what we call the main sequence here, the blue points. And a few of them, you can find them on the starburst region just above. So they are forming stars more efficiently at a given stellar mass. And then you find here in red, the red and dead galaxies, so the passive one we just showed before. And in between, in green, you have the galaxies in transition. So it's another way to look at this. And it's very interesting because the existence of this main sequence tells you that most of the galaxies form their stars through secular events. It's something that is smooth, and they are forming their star continually, I mean, through a secular process, and not through violence events and frequency events. If it would that be the case, then you would have galaxies everywhere on this plane, but this is not the case. So people have been trying to constrain this star-forming main sequence from different wavelength range, from different population at different redshift. I just show here examples, but it's just a few examples of what have been done. You can see on this work the main sequence, which is in black, and you see the starburst line here. You have different definition for the starburst region. Here is the main sequence, and some people define the starburst to be 4 times above the main sequence. So you start to have this kind of study. Here you see different relation at different redshift. You can see that it's a result indeed that the normalization of this star-forming main sequence increases with redshift. So you have here on the Schreiber study, you have galaxies at low redshift nearby here in blue. And when you go to high redshift, this normalization increases. And the slope at the end also changes a bit at the high mass end. So there have been studies really to understand this normalization, the slope of the main sequence. But what is striking is that the scatter that you see here of the main sequence is found to be relatively constant across cosmic time and all stellar mass range. So it's about 0.3 dex. So it's very interesting because we want to understand what is the origin of the scatter of the main sequence. What is it constant more or less over cosmic time? So it could be due to I would say noise in the way we measure star formation rates and stellar mass in the different techniques, the different observation that we have. But most studies seems to find this scatter every time the constant with approximately the same value, but it's robust against the different method that you use normally. So there seems to be a physical origin of the scatter of the main sequence. And this is something that we are really interested in and we want to understand. Some people think that this scatter could be due to short-term variability into the star formation history of your galaxies. Instead of having just a galaxy forming star and then experiencing a starburst, you can have galaxies doing some very short-term fluctuation like this. This is something that could be possible. Other interpretation could be that this is the imprint of a long-term differentiation that is due to the initial mass of your galaxy, especially its dark matter halo mass. And then because of this and different growth history, you end up with this kind of scatter. So the main question that I would like to ask is, can we follow galaxies in their movement on the SFR mass diagram? Can we have an idea that this galaxy here where was it before, like a few hundred mega years ago? Was it in the starburst region? Was it still here on the main sequence? Did this galaxy went up from the passive one? It could be possible. So this is the type of question I would like to answer. So this is a cartoon that show the typical thing that I'm trying to put constraint on. You can have these galaxies growing up here on the stellar mass, on the SFR mass diagram, just slowly growing up quietly, and then at some point quenching. You see how here becoming passive. Or you can have this galaxy coming like in a merger type of event, and then after the starburst you can say, well, is this galaxy going down, crossing the main sequence, and at the end ended up to be passive? Or can this galaxy then go down after the starburst but stay on the main sequence? It's a question. Can a galaxy just make this kind of movement between in the scatter? So just what I explained earlier, but also what we call rejuvenation. Can galaxies in the passive regions come back on the main sequence? So actually to put constraint on that, we want to probe quick movement, quick variation. We are talking about typical scale of, like, if we are talking about less than 100 mega years, you can have mechanisms like formation and destruction of giant molecular clouds that could provide and imply this short-term variability into the SFH of the galaxy, star formation history. And at intermediate scale, between 100 mega years and 1 gigayears, you can have a lot of mechanisms such as galaxy merger, disk instabilities, winds, that could explain some variation here on the scatter of the main sequence. So what would be a killer to the problem? It would be the spectroscopy, because with spectroscopy, you have the Balmer lines, you have the Balmer break. You can really probe the very recent star formation activity of your galaxies. But unfortunately, spectra at the moment, before the launch of next generation facilities, spectra are available for like 1% of the cosmos field. So for people not familiar with cosmos, it was on one of the largest extragalactic field that we have now, with almost a million source. So we don't have spectra for this. At the moment, we are stuck with broadband photometry. And also because we need to probe very short time scales and really we want to be able to catch the galaxies while they are doing this really short movement. We need a lot of statistic because we are probing a phenomenon that is very short in time. So of course you need a statistic to identify and pinpoint these galaxies. So the classical approach to recover the star formation history of galaxies is SED modeling. SED is for spectral energy distribution and of galaxies. And what we do generally, we have observation from UV to infrared and almost radio, and we build models of SEDs that we adjust to our data, and we derive parameters such as star formation rate, stellar mass, dust attenuation, infrared luminosity, etc. So the classical approach, I would say, the first step is to make an assumption on the star formation history of your galaxy. And we need to be simple because it's a complex thing. So usually we use analytical star formation history, like exponential declining, delayed exponential, constant star formation history. And this is convolved with a typical stellar population model. And here you have your emission of stars convolved with your star formation history. But then you need to take into account the attenuation implied by dust that is present in your galaxy. So the effect is that you apply an attenuation law that will reduce here, and the energy that you see between the two blue curves is re-emitted in infrared by dust. You can add on top of this the emission lines and also radio emission from star formation, and you can also on top of this add the contribution of an AGN. So this is typically what SED modeling could do, all of them. And here we use in Marseille SIGAL that we have been developing. That is public and everybody can use it. And we are improving SIGAL, and recently we added a non-parametric star formation history that I won't have the time to mention here, and also the X-ray modeling of AGNs. So we have really a complete tool that model everything from X-ray to radio. So this is what we call the classical approach. So the typical star formation history of galaxies look mostly like this. If you make assumption on if you look at the star forming main sequence of galaxies that I showed you, and because of this variation of the normalization with redshift, you can reconstruct the typical star formation history of your galaxies. And you can see that if the seed of your galaxy is very massive, it will increase, and rapidly it will quench, and more rapidly that galaxies that are less massive. As you can see here, you have different things. But galaxy star formation history is not that simple. They are expected to be more stochastic, and you can see here example of star formation history. So you have this smooth envelope that I just showed you, so like a mean star formation history. But if you take galaxies one by one, you can see all this variation. This is another example from a semi-analytical model, and you can see all the spikes due to different starburst events. So if you want to model one galaxy and recover its star formation history, you have to be able to probe these different events. So as I explained to you, in most STD modeling code, what we use is a typical analytical function, such as here, the delayed one, the tau delayed one, it's the purple one. And here you have the exponentially declining one. And if you compare to the true star formation history of your galaxy, what is striking is first that the exponentially declining one for this galaxy does not represent the best is not a realistic estimate of the star formation history. But the delayed one managed to reproduce the average envelope of your star formation history. But you don't see, you cannot recover, of course, because it's too simple, you cannot recover all the typical variation. And there is another problem using parametric star formation history, is like if you use the delayed on a typical star formation stellar mass plane, so this is the main sequence here with the scatter, this is a typical sample, you can see there is a gradient of age. Here, galaxies being in the lower part of the main sequence are older, seems to be older than galaxy in the starburst gradient. But actually, this is a bias from implied from your analytical model. If you take the delayed here and you allow for flexibility at the end of your model that you put in your STD modeling code, you see that this gradient of age completely disappears. So this means that there are some biases implied by this very simple function. So allowing this flexibility is one step to get rid of one of these biases. But when you do this, when you add a flexibility, of course, you add more free parameter to your model. And one of the questions is to understand, do you need for all galaxies to add this extra parameter? Is it the right way to go to recover star formation history of galaxies? So this is one question that we wanted to ask. And to do this, we collaborated with a statistician of a mathematical laboratory that is close to ours, that are specialized in what they call approximate Bayesian computation. So I will explain quickly, but it's a method they used for other field, like for biology, when they studied genetic of population. It has been used in different occasions, and then with the statistician, we tried to see how we can use this for, I won't say the genetic of a galaxy population, but for recovering the history of galaxies. So this method will help us to perform model choice. And in this case, it will help us to understand which is the star formation history that best represent our galaxy's fluxes. So here we want to discriminate between what I showed you, the delayed, simple delayed that provide a bias in your measurement, and the delayed plus flexibility that allows you to model galaxies that are experiencing a starburst or a quenching. So basically how it works, first you choose one of your SFH model, tau delayed or delayed plus flexibility, and you build a whole set of SCDs with a large range of parameters. You have all your SCDs and you convert them into a set of filters, which is typically the set of filters of your galaxy catalog with all your observation. And then you compute the distance between the summary statistic of the simulated SCDs and the one of the real data. In this sense, this method is really close to, it's typical the KNN machine learning method. However, we can generalize ABC to other algorithms that are more efficient than KNN and keeping the statistical properties of this method. So this is what we did. And at the end, we used machine learning classification that is called XGBoost. And as you can see, in terms of computation time, it was way better than a typical KNN method. So we have this method that provides us an answer on what is the good models, SFH model for your galaxies. So since we simulated a huge library of SCDs, we knew for each SCD what was the one we used, if it was the delayed or the delayed plus flexibility. And then we could test the method and see if it was wrong or right in recovering the good SFH model. And the result, the error rate of each method we tried is here. And what you can see that in green, we have SIGALs, which is the typical classical approach that we had until now. And SIGAL for this exercise provide an error rate of 29%. And with our method, with XGBoost, we managed to go down as 21%. So it was quite efficient and something that we wanted to keep investigating. There are some limitations, of course, because the statistician didn't have they are not used to work with astrophysicians, and also the typical problems, if I can say, that we have particularities that we have with our galaxy catalog. For instance, we have the different signal to noise ratio for different flux and different galaxies. We have galaxies that are not observed in one band because they are too weak, not detected, or because they are just not observed in the field. And also we have the redshift problem that shift every colors with the distance. So these are problems from for which the statisticians have not the answer yet, and this is still under investigation. We have some students, statistician students, working on that to go a bit further in this method. So these are the results that the methods provide. In the x-axis, you have the probability of a galaxy to have experienced a starburst or a quenching in the last 500 mega years. And on the y-axis, you have this parameter, which is called RSFR, which is just the ratio between the SFR observed, the star formation rate observed of your galaxy, and the star formation rate it had before the event. So everything that is above 0 is a starburst, and everything that is below are quenched galaxies. So you can see here the distribution, and this is the test sample. On this test sample, we had 50% of our galaxy which are supposed to be using delayed plus flexibility, and half of the galaxy which has just a simple delayed. And we cover quite well the results, and we have for galaxies that have the highest probability, you see that we recover starburst, a quenching galaxies, as long as the ratio is more than a factor of 10 for starburst, or less than a factor of 0.1 for quenched galaxies. So this is what you can see here. This is the sensitivity of our method. So we applied this to the Cosmos field, which is a large field of extragalactic sources, you can see here. And we had 42,000 galaxies. We keep a quite narrow range of redshift because I told you that the method is not yet very well calibrated for the impact of redshift. And we also use a very strong signal to noise ratio because we need to investigate the impact of the signal to noise ratio on the method. And this is the distribution of the real galaxies. It's the same thing that I just showed you. This is the probability of a galaxy to have experienced a burst or a quenching very recently. And what you see in green is what we call the Jeffrey scale. It's just a typical scale telling you if the probability provides you a decisive information, very strong information, strong, substantial, or barely worth mentioning. So if you see here that majority of galaxies have a probability below 50% to have experienced a recent burst or quenching. So this is, of course, what we would have expected. If not, the main sequence wouldn't be what it is now. But we wanted then to focus on these galaxies for which we are almost certain that a burst or quenching, just a quenching of galaxies or star formation rate just happened recently. So this is the work we have been doing, and we were more interested in rapidly quenched galaxies, so not starburst. We focused in quenched galaxies. So we use this probability that the ABC method gave us, and we know for these galaxies that something happened, a quenching happened in the last 500 megayears. Now that we know this information, we know the right star formation history to be used in our code, SIGAL, and we used it to derive the physical properties of the galaxies. You have here two examples of galaxies, and you see clearly the quenching at the end that was expecting from the probability. So when we use SIGAL on the sample, so we use the probability to select the galaxies, but the code doesn't know the probability when it fits. So this is a confirmation of what the method gave us. And if you look at an optical spectra that we found on some archives, you see that there are no strong emission lines. That confirms the fact that the galaxy is supposed to be quenched recently. You don't have neither strong absorption lines that would have indicated quenching that would have been much older than what we thought. And this galaxy is very interesting because you see that there is this strong quenching. You have the information from the LCD modeling, you have the information from the ABC method, but you see there is some infrared measurements and also radio. So this is very interesting to understand what's going on here. And it is a galaxy, this is confirmed by the spectra here. So it's a galaxy that needs further investigation to understand what is the role of the infrared here. Is it due to all-star population? But you have this radio point here that could say that there is star formation still going on. So is it obscure star formation? What is due to this? So this is a very interesting question that we need to answer. So what we wanted to do after, because as I mentioned earlier, our main goal is to be able to recover the position of the galaxy on the main sequence, to recover where they were before this quenching, before it happens. So these are our candidates for which we are quite certain, this is our fiducial sample, that they are rapidly quenched. And if you look, you remember this is the typical SFH we assume, so a delayed plus a quenching. So when you have this, you can say, okay, our galaxy is here now, but before the quenching, it was here. And so what was its property here at this point? What was its infrared luminosity? Where was this galaxy? So this is what we try to show here. We try to place back the galaxies before the quenching, and you can see they were on the main sequence, and after that they were going down. So this is one step toward answering the question that are driving our research. And we could go a bit further. We had, of course, to make some assumptions that the attenuation from dust did not evolve since the quenching of the galaxy. And we used this long-term ASFH that I just showed you to try to see what was the infrared luminosity of the galaxy before its quenching. And you can see here, these are the sample of the cosmos galaxies. But as a fiducial sample, we use galaxies from the Virgo cluster. And I told you in the introduction that some galaxies were suffering RAM pressure stripping because of the impact of the intracluster medium that was stripping the gas out of the galaxy, and this was causing a rapid quenching. So this is a typical sample from the Herschel reference survey that we know very well. These are local galaxies. We know they are quenched. We know why they are quenched. So this was a fiducial sample for us. And these are the blue squares that you see here. And what is interesting is to see that if we assume, so this is the ratio between the infrared luminosity now as it is measured and the infrared luminosity before the quenching as we estimated. And on the x-axis, you have the age of quenching. So this is a recent quenching like happened 10 mega years ago, and this is an old quenching that happened 1 giga year ago. So the cosmos galaxy, they are very close to, they're quenched very recently, and Herschel sample from the Virgo cluster, they quenched at a longer age, and these are typical age. This is typical value for RAM pressure stripping. So this is something measured by SIGAL. So it's another indication that we are doing something that is not crazy, because we find the typical time scale of RAM pressure stripping. And if we assume, this is completely arbitrary, but we said, okay, let's assume that the infrared luminosity after quenching decrease as an exponential, decreasing exponential, so with different tau. This is what we showed here with the lines. You see that the mechanism responsible for the quenching of the cosmos galaxies implies that the infrared luminosity decreases faster than the mechanisms responsible for the Herschel reference survey, so the Virgo cluster galaxies. So this is what I wanted to show. So this is what we wanted to, this is how we wanted to recover the galactic past properties. And I think, yes, I think I'm done now. So this is my summary. So just to rapidly wrap it up. So we aimed at understanding the scatter. So here of the Starforming main sequence, try to understand and discriminate the different evolutionary paths that you see in different colors. So to do that, we use first classical SED modeling techniques, and then we saw that there were technical aspects that maybe was preventing us to accomplish this. So we use a statistical method, the approximate Bayesian computation, to help us find the appropriate star formation history to be used to derive our galaxy's properties. This is what we did. And for galaxy, we managed to recover and rewind a bit their path across the star formation main sequence, and recover their past properties. So this is just a step forward, a final step, and we have more work undergoing, especially trying to add a non-parametric star formation history, which I think will be a big step for work. And that's it.
Thank you, Dr. Ciesla, for the very interesting talk. We will now have time for questions from the audience. If you joined us on YouTube, you can put your questions in the comment section. And if you joined us here on Zoom, please raise your hand and ask your questions. So we have questions from YouTube. I will start by there. Ubu asks, have you found evidence on these recent star formation events that could suggest a non-canonical IMF top heavy?
No, we didn't look at the IMF. We only have broadband photometry, and I'm not sure we can constrain anything on IMF with this. When we do our SED modeling, we have to assume one IMF. So it's a typical, I think we use a salpeter. So this can be changed, but we didn't investigate it at all, this.
Okay, so there is another question also from Ubu. Regarding the risk, regarding the SED fitting and objects that are not detected in some bands, could you mention some solutions that you have explored so far to solve this issue?
So for classical SED fitting, right? For when we do SED fitting. So when we do SED fitting, well, if a galaxy have a lot of bands when it's not detected, of course we disregard it, and usually the fit is either too good or not good. So it depends. But you see, we have diagnostics that allow us to pinpoint these galaxies. And we have diagnostics also to see, as the whole catalog, the whole bench of galaxies that you're studying, if the parameters we derive are constrained through mock simulations. So this is how we test. If we can constrain the parameters, so it means that even with the non-detection of galaxies in given bands, we test if our parameters are constrained and if we can say something about them. For the machine learning method, this is a problem, and this is something we are currently working on with the statisticians, and we need to find a way. Their first approach when you talk to them is to infer the missing data. So it's a bit dangerous. So it's something we need to discuss with them, because they have their mathematical approach, but we have our observational bias. So we need to discuss with them. They would tend to say, okay, just infer the missing value and then run the method. It's something that it's still in investigation.
Well, thank you. Thank you, Ubu, for your very good questions. More questions? While we wait, I will actually ask you a question. In your, you selected more than one method in machine learning to classify your galaxies. What are the typical errors that are holding it to the 33% of error rate?
What are the things that are?
Yeah. Yes. What do you think it's causing this error? Of course, we also will have some error, or is it some properties that are not being modeled? Or?
So it's quite difficult actually to estimate the star formation history of galaxies. You have the attenuation, which can cause like a degeneracy. If you don't have a good estimate of the attenuation, then you're degenerate with some star formation histories that are different. Also, you can have, if you have very, very short quenching or burst, something very subtle, I would say, like an increase of the SFR, like by a factor of 2. So this is very weak and difficult to recover. So I think some error comes from that. And you can see, if I can show here, that it's not, if it would have been perfect, you would have like this going just here close to 1. But you see that this will, show you that the method does not manage to see and to probe very tiny variation of burst or quenching. So something like it's typical, a factor of 2, or quenching just divided by 2 the star formation rate. It's too subtle. for the method to pinpoint it. And I think this is causing the error that you see. In addition to the typical different attenuation, different other parameters that are playing a role in the galaxy acidity.
Yeah. Thank you. That's very nice. More questions? Also, coming back to these questions, we usually have to have a margin of error, because if we don't have, our model becomes too fit to a single case, I suppose.
Yeah.
Also.
Yeah.
Okay.
And also, from my understanding, is that since the delayed model is nested with the delayed plus flexibility, I mean, the delayed model is a particular case of the delayed plus flexibility. My understanding is that this is the typical distribution, what you expect from, this is what I understood from my colleague from statistics. So they were not surprised with this distribution.
Oh, thanks. That's nice. Well, still have time for more questions. Well, while we wait, I have another question. We have you showed us. I saw in your plots that you're using broadband measurements to fit the NCDs. Are there surveys that will be dedicated to get more data, to explore these regions of science, or will a survey like LSST be useful to you?
So at the moment, well, we need statistics. So today, the catalog that provides the more statistic is Cosmos, with a large range of bands. I think it's like 30 bands or something like this. So combining a good sampling of your SED, because this is important, and also a good statistic, today, Cosmos is the best. And what will be very, very useful is that Cosmos will be observed by GWST. So there will be near-cam data, very deep. So this will, I think, bring new information, and I think would be a step forward in our study. So we have a PhD student that just started to work on this. So applying this kind of method and also others to reconstruct the star formation history from Cosmos web program. So I think this will be nice. LSST, of course, will be nice, because in terms of statistic, I think it's unbeatable, but we have will be a limited range of band, and it's difficult. You need to probe this. You need to have a good sampling of the rest frame UV, a good sampling of the rest frame near infrared, and also in between, because you want to have the shape really to probe events. So you really need to sample intermediate age stars. So I would say at the moment, Cosmos Web is the thing that we want.
Yes. I was imagining that, because it's quite there are a lot of measurements in the near infrared also. So.
Exactly.
LSST will actually cover very well that region. I cannot cover that region actually. So more questions? Okay. Well, if there are no more questions, we will now wrap this up. This presentation will be available on our website and on LIneA's YouTube channel. Thank you everyone for attending, and a special thanks to Dr. Ciesla.
Thank you very much for receiving me.
Yeah. And everyone, have a great day, stay safe, and I hope to see you all again in our next webinar. Thank you very much.
Thank you.